Welcome everyone to the session on performance evaluation and benchmarking of AI systems, presented by Shriyari Karnam from Intel Technologies, and we have Judajit Datta from TCS along with us. And Intel is a steering committee member of the UXL Foundation, right? And during the session, if any of the participants have any questions, please do post it in the Q&A, and we will be more than happy to respond to that during the session. If not, at the end of the session, we have a dedicated 5 to 10 minutes for the question and answers. So please feel free to post your questions in the Q&A panel, right? And so here we start with the session. Over to the speaker, Shriyari.
Am I audible? Yeah, I'm audible, right? So, hello everyone. I'm Shriyari Karnam. I'm excited to be here today. A bit about myself. I come with over 2 decades of experience in the tech industry, and I have focused extensively on HPC AI, particularly in software enabling and optimization world. I work with Intel's oneAPI team, where my focus is on enabling and optimizing AI applications for Intel platforms and improving the robustness of performance libraries and compiler runtime components. My areas of interest include HPC AI, computer architecture, supercomputing, and heterogeneous computing. Let me also introduce my industry partner, Judajit Datta, who is working as a research and innovation lead of HPC and computer architecture in TCS. He has over 2 decades of experience in HPC supercomputing and performance engineering areas. With that, let's get into the session. So, agenda. Today we'll explore key concepts in AI system performance with a focus on evaluating and optimizing these systems for scalability and efficiency. We'll start by looking at the tech stack of AI systems and then dive into performance evaluation techniques, touching on metrics that matter and strategies for improving efficiency. From there, we'll cover the benchmarking hierarchy and approach, which guides how performance is measured across different levels of complexity. We'll wrap up with tools available in oneAPI ecosystem to support these efforts and key takeaways from this session. So this AI system tech stack consists of layered hardware and software components that form the foundation of today's AI advancements. We'll begin our discussion with the foundational hardware layer and then progress upward through the stack to explore how each layer contributes to the overall AI ecosystem. Modern deep learning AI models require millions of matrix operations, and we need to parallelize these operations to make AI computationally feasible. That's where CPUs, GPUs, and specialized accelerators come into play. They are designed to handle these parallel matrix operations quickly and cost effectively, and making AI economically viable. Storage plays an important role across the entire AI lifecycle. It stores training datasets and model checkpoints essential for efficient training and also used for storing and delivering model artifact for inference services by providing data for batch inference. Interconnect also plays a crucial role in the scale up and scale out of AI. Low level and compatibility software layer plays a critical role in interfacing high level AI frameworks with the underlying hardware architecture. oneAPI ecosystem provides essential APIs, tools, and runtime environments that optimize data transfer and execution across diverse hardware platforms. By leveraging these tools, developers can fine-tune performance, ensuring efficient utilization of compute resources for AI workloads. AI compilers transform and lower the computational graph of AI frameworks into an intermediate representation where they apply various optimization techniques such as fusion, memory reuse, and parallelization. This optimized IR is then compiled into hardware-specific code tailored to exploit the capabilities of target architecture. At the top of AI tech stack, applications and workloads drive performance across the entire system. These AI applications utilize models and algorithms that push frameworks like PyTorch, ensuring they operate efficiently with underlying compilers like OpenVINO and oneAPI ecosystem. The workloads generated at this level are highly computational and memory intensive, making them crucial for testing and optimizing system performance. By exercising both software and hardware, these applications help identify bottlenecks, tune performance, and ensure scalability across CPUs, GPUs, and other accelerators in the AI ecosystem. Now that we have covered the AI systems tech stack, and its key components. Let's move on to discuss how we measure its effectiveness. Performance is a core currency in AI, and benchmarking provides the tools we need to empirically evaluate and optimize this performance. In the field of AI, understanding the performance is critical. It begins with impact assessment by identifying bottlenecks that hinder efficiency, provide guidance for tuning to unlock the full potential of AI models. Performance debugging is crucial as well, revealing inefficiencies like memory bottlenecks that slow down process. Evaluating resources ensures the right tools are available for large scale tasks, while standardization provides consistent metrics enabling fair comparison and encouraging best practices. Together, these elements create a robust framework for optimizing AI performance. So, benchmarks are crucial for evaluating AI performance because they offer a variety of standardized workloads. These workloads vary in size and input datasets, allowing for a comprehensive assessment of how AI systems perform under different conditions. So let's move on to performance evaluation techniques. Performance evaluation techniques can be grouped broadly into two categories: direct evaluation and modeling. Direct evaluation involves testing on physical hardware, providing hands-on insights into how an AI system behaves in the real world. In the modeling category, there are two key types. Simulation modeling, which builds a virtual system to mimic real-world performance, and analytical modeling, which uses mathematical representation to estimate the performance. Both are critical for predicting scalability, energy efficiency, and overall performance in the AI systems before deploying on the physical hardware. When working on AI training, teams often face challenges in reproducing issues in scaled out distributed environments, particularly when they lack access to similar infrastructure. This can be complicated troubleshooting, especially as experimenting with new configurations can be both time consuming and costly. Modeling provides a solution by allowing teams to simulate different scenarios and configurations. This not only facilitates efficient experimentation but also enables the identification of performance bottlenecks, optimal resource allocation strategies. Once the simulation is complete, the identified configuration can then be tested on actual hardware, ensuring robustness and performance before deployment. This approach not only saves costs but also supports effective hardware-software co-design, ultimately improving the scalability of future AI systems. Current benchmarking practices encounter challenges, including the high costs associated with running full workload benchmarks and difficulty of pinpointing specific bottlenecks in compute memory and network. This is particularly relevant in the context of distributed AI training, where identifying and addressing these bottlenecks is essential for optimizing performance across large models. As teams work with extensive datasets and complex architectures, effective benchmarking becomes crucial for ensuring that resources are used effectively and that potential issues are resolved early in the development process. So there's a trade-off between direct evaluation on the system and creating a model and executing the techniques on that. Understanding key performance metrics and efficiency is essential for evaluating the effectiveness of AI systems. While I won't cover every single metric, I will highlight those that are particularly significant for assessing the performance of AI systems. Flops or floating point operations per second serve as a benchmark for computational performance, indicating the capacity for rapid training of large AI models. We have TOPS also for inferencing. Memory metrics include capacity in gigabytes and bandwidth in gigabytes per second. These are essential for managing substantial dataset efficiently. Arithmetic intensity, defined as the ratio of flops to bytes transferred, highlights whether a workload is compute bound or memory bound. Optimizing resource allocation, etc. Energy efficiency is measured in picojoules per operation, which is critical for maximizing performance per watt, especially in edge AI scenarios. Finally, latency and throughput are vital metrics for dynamic AI applications. Latency quantifies response time, while throughput measures task processing capabilities. Both are crucial for AI application. The roofline model crucial insights into AI system performance by illustrating the trade-offs between compute and memory resource. Roofline indicates whether a workload is compute bound or memory bound while guiding the optimization. If a workload is compute bound, enhancements in computational capabilities can yield significant performance gains. Conversely, if it is memory bound, increasing memory bandwidth or optimizing data across patterns will be key. This understanding helps developers make informed decisions, ensuring that AI algorithms effectively utilize available hardware resources. Thus, we can maximize performance in both training and inference scenarios. In next slides, actually, I'll tell you how to use roofline and what tools we have to, which will guide us through the roofline modeling. Is the next slide visible? Oh yeah. So slide number 7. In this slide, we will discuss about 3 key areas: arithmetic efficiency, memory utilization, and the concept of ineffectual operations. Each of these sections highlights different aspects of how to optimize performance while minimizing resource consumption, which is increasingly important in the context of modern large-scale AI models. Arithmetic efficiency, when working with large AI models, selecting the right data type can drastically impact both speed and energy. In practice, I have found using mixed precision like FP16, where appropriate, significantly speeds up training while cutting down on energy consumption. Floating point operations are resource heavy, so whenever possible, leverage integer operations. In this way, we can balance precision and performance, especially in training environment. Coming to memory efficiency, keeping data close to compute units has been a game changer in optimizing AI models. In real-world applications, minimizing data transfers by reusing data on chip has helped reduce power consumption and improve the throughput. Off-chip memory is typically slower and costlier, especially for DNNs where weights are fetched layer by layer. Making sure data is readily available near processing units boosts model efficiency, something that's key in large-scale AI projects. Third, swim lane ineffectual operations. In my AI projects, handling sparse data efficiently was critical. Skipping unnecessary calculations like during pruning has not only speed up inference but also reduce the compute load. By leveraging formats like compressed sparse column CSC, I was able to manage to optimize the storage and representation of sparse weights along with the activation, leading to better overall performance, especially in resource constrained environments. To summarize, achieving efficiency in AI is about doing more with less. It involves reducing operations where possible, using smaller data types like mixed precision, minimizing data movement to save time and energy, and reusing data effectively. By leveraging sparsity and efficient data storage formats, massive AI models can be run faster and with less hardware strain. These strategies make large-scale AI both feasible, powerful, and optimizing performance while keeping resources in check. Scalability and training time. As AI models grow in size, managing scalability becomes essential. Model parallelism allows large AI models like LLMs to be split across GPUs, ensuring that different parts are computed simultaneously. Data parallelism uses all-reduce or ring all-reduce method to keep model weight synchronized across multiple GPUs, which enables faster training. Pipeline parallelism further enhances efficiency by model strategies and balancing GPU workloads. These parallelism strategies significantly reduce training times for modern LLMs, allowing us to scale and optimize models without sacrificing performance. So far, we have covered performance metrics and efficiency strategies that are critical in optimizing AI systems. Now let's shift focus to benchmarking. This is where standardization comes in, offering a structured way to measure performance across different systems and workloads. We'll explore the benchmarking hierarchy and how it helps us consistently evaluate and compare AI performance. Benchmarking in AI systems spans several levels, decreasing in complexity and cost as we dive deeper. At the top, the use case level represents real world applications, such as language models deployed for chatbots or autonomous systems. Moving down, application benchmarks measure system performance as experienced by a specific application. Think of LLMs evaluating how well a GPU handles massive inference tasks. Macro benchmarks assess broader operations, combining multiple components like data preprocessing, model training, and inference into one task. As complexity narrows, program kernels target essential loops in AI workloads like GEM, matrix multiplication, etc. Micro benchmarks go even deeper, focusing on individual components like memory or compute, evaluating their isolated performance. Finally, synthetic benchmarks mimic the workload profile of real world applications, but in a controlled setting to predict the system performance. In AI, especially with large models like GPTs, these benchmarks allow us to assess compute, memory, and bandwidth efficiency at every level of system, informing both hardware tuning and software optimization. Standardization of benchmarks. In the landscape of AI benchmarks, communities like ML Commons and Spec play crucial roles in standardizing evaluation methods. ML Commons through MLPerf is essential for assessing AI training and inference performance, particularly in real-world applications. Tech ML focuses on machine learning workloads, offering valuable insights at the application level. Additionally, TPCX AI provides a framework for evaluating AI-driven decision-making process in real-world scenarios. While benchmarks like LinPack and HP LinPack are not tailored specifically for AI, they remain relevant by providing foundational numerical performance metrics that can support AI system optimization. Understanding when to use these benchmarks ensures that both computational and memory efficiency are prioritized. Intel also has open source version of benchmarking suites like Velocity Bench and others. And OpenVINO and other tools have native benchmarking system inbuilt. So you can refer tools section under oneAPI to check various oneAPI benchmarking utilities as well. Benchmarking approach. So as we transition from discussing performance efficiency and benchmark hierarchy, it is essential to explore the end-to-end benchmarking approach. This structured methodology ensures that every aspect of AI system performance is rigorously evaluated. By defining clear goals and systematically selecting metrics and evaluation technologies, practitioners can derive meaningful insights. The process is iterative, allowing for refinement and adoption as new workloads and systems emerge, ultimately leading to robust and reliable performance assessments for AI applications. We can refer to this offline as well. So now our partner, Jujadit Dadda, right, he will talk about his experience with respect to leveraging oneAPI tools, utilities in his applications, and he will talk about his experience on oneAPI.
Audible right now. So thanks a lot, Srihari, for these great presentations where you set the background for us. So yeah, we basically see the AI system because AI system is still not properly defined. We see the AI system as a two AI computational systems and another is the AI application systems. So of course, underline the both system having the computations available over there. In computational system, there is a two part. Of course, it starts from the hardware software key design and the device as well as system design itself. Another part is the kind of AI engineers who is going to use the platform. It can be device, it can be systems and the tools available of the trade, parallel processing frameworks, abstraction level, domain specific framework like TensorFlow and other compilers. These are the areas to be and optimizers. And of course, underline the different kind of device and the device class available. It can be from the tiny systems to a kind of a big supercomputers. And then also one of the part is the AI system for the AI application systems where real world challenges can be solved by artificial intelligence. So that system also, it is one of the part, and here model it's a small part of the game. Majority of the tasks we have to done with the data collection technology. There are several types of modeling systems and the inference and others. So as we are talking, there is a means there is a news from the AI community that Professor Hilton got the Nobel Prize for the physics. Its application and application to be for the there could be probable applications for the physics of the AI, and it is AI augmented simulations and all other things. Especially for the large scale simulations and large scale AI, we can see two distinct paths over here. One is the large scale models and large scale model, vision model and language model, and the multimode, and another part of the AI augmented simulation for the different types of application domain. Now here lies the questions. If you take that particular samples and other, even for the other device classes also, how do define why do define the performance strategy over there? Means how do the performance over there? It could be application level performance, it could be a performance of the system level, or it could be device level. So COD already discussed of the different types of the benchmark where exactly we can use it, but also we have to do some kind of strategic way to complete the ensure the performance, because it's a kind of a this experiment cannot be done in an isolation manner. It should be a kind of targeted towards kind of a workflow. So here we provide some kind of workflow and framework for everybody. So first we need to set the goal, where exactly we need to provide, where exactly we are looking for. So is it a kind of a checking of the device or the systems, or the any optimizer systems, or even between the AI model, or even the application itself. So that goal should be very clearly mentioned over there. Then once you complete the goal, we can give the list of the services and the kind of outcome we require. Of course, it should be also properly documented before we start. Then we select the metrics. What kind of things we are going to, what kind of metrics by key performance indicator we have to look out, and using that we have to collect the data. And to get the metrics, what kind of parameters will be possible over there, and select of the factor to the study. Now we start the evaluation technique. The evaluation technique depends on the kind of work we are doing. Sometimes it is directly to the system, as theory already mentions, and another part is the simulation part. Sometimes in a very large scale system, it's very difficult to judge what kind of system we are going to use. So there is a different types of simulators people are using for evaluation for the workload, how much system can be discovered, and other things also. Second part, the analytical method, the way you data collect, we describe the data, and then we understand the data, and top of that we have to go. Another part before we start, that's the selecting of the workload itself, because there could be a several representative workload. So what could be the best possible workload for my application? Is it application itself? If it is a very big application, it would be a lot of challenges over there. So there now we have to select different technique to apply for the selective selection of the workload, and then we decide for the design of the experiment. So this is the experimental process. Now analyze the interpret the data, the already data we have collected from our targeted, and this is these things. This is the one way to report the data, as well as if it is not satisfactory, we have to repeat the experiment. Is there any bottleneck over there or not, or any problem we facing out, or any challenges we face out for the performance benchmarking itself. So this is as a whole approach we used to follow for the benchmarking. So I go to the next slide. Almost all the vendors available over here, including, so of course everybody having some kind of strong and bottleneck strongness, as well as weakness also there. Overall, pretty much everybody is a kind of a similar space and the very capability. So oneAPI also provides similar kind of approach over there. So robust library of like one DNN, and the profiler, like these are all very old and as well as a very industry standards tool like the Advisor, oneAPI tools also, unit trust, and as well as performance VTune also. So these entire ecosystems together, the collection of the data, performance system, bottleneck of the system, we work into proper way. So this is as a whole. And one of the major things we would like to incorporate over here as a part, that the kind of benchmark towards a device and the system will not be always provided properly. Sometimes we have to, there is a several benchmark association with the standardizations and events other also. So sometimes it's difficult to get where shall we look out for that. So sometimes this kind of informations in the ecosystem would be more beneficial, because this is one of the part probably most of the people we are use, but little bit neglected area to be look up. So this is as a whole of the system to be developed. Yeah, over to you.
So we are almost at the end of the. So what do we conclude, and what are the key takeaways? In conclusion, we can say the journey through AI systems reveals that the performance evaluation is not only merely a checkpoint. It is a ongoing commitment to excellence. Right. Key takeaways highlight that critical importance of understanding performance metrics, adopting robust benchmarking approaches, and leveraging standardization to drive the innovation. Achieving computational and energy efficiency is critical, especially in the context of scalability for large models. So, by embracing these principles, practitioners can ensure that AI systems not only meet today's demands, but also prepared for the complexities of tomorrow's challenges. A little bit more on oneAPI tools. OneDNN accelerates deep learning performance, right, by optimizing critical operations, ensuring faster model training and inference. So the other one, OpenVino, enables seamless deployment of high performance AI inference across various hardware platforms, maximizing the efficiency. With oneAPI AI tools, developers can streamline their workflows, tapping into advanced capabilities for model optimization. So we have seen the roofline model, VTune Profiler, VTune Advisor provides deep insights into performance bottlenecks, enabling fine-tuning of applications. So Intel Advisor helps in vectorization and optimization strategies, while Unitrace offers a comprehensive view of application behavior. Together, these tools empower developers to maximize the potential of their AI systems and help driving innovation and efficiency. Yeah, we are at the end of the session.